Yes. Okay, finally, I managed. Took 5 minutes late, I'm sorry. Your patience. This is week number 5. I was asked for books to read up, and I compiled a list. And this is just a short list of all the possible options. It's things that I know and selected personal choice, but it doesn't mean that they are better than things that are not on the list. I am using Ebenhäuser, this is in German, tutorial on QFT theory, if I need to fix my notations. So this is, for example, one that uses the metric plus, minus, 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 and of course Pascal Schröder as the standard, my standard reference. But all the others are good too. Probably they use different conventions. Minus, plus, 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 and then in any corner where you have to make a choice, you basically double the possibilities, right? So even if someone else uses the same metric, then they use something else for the spinors or so. And just look at them and decide what works best for you. Given that I have this on screen, I am going to scroll through these dates. We have fixed the exam now to the 24th of February. It's going to be written. Now I want need this right now. We've been talking about representations like Lorentz transformations and representations of the Lorentz group. And now that we know how things transform, let's use some of those things that transform in a particular way and write some equations of motion. I call this, I guess, 4.4 relativistic field equations. So just to give you the path, in this course, we are aiming at quantum electrodynamics. This is the quantum field theory for electrons, and then they come with the positrons and photons. So we need something that represents the electrons. These are spinors. In fact, they're Dirac spinors. And the photons, these are vector fields. So we will have something that transform under certain spinor representation and vector representation. And then we'll also discuss always along the scalar fields, which are not part of electrodynamics, maybe scalar electrodynamics, where you replace the electron by some fictitious scalar particle, but we still discuss it because it's simpler. It's the prototype of a quantum field, and then you add more indices and you get more complicated. So these 3 things will be discussed now every time in this order: scalar field, spinor, vector, and then we go first classical equations of motion, then we go to the Lagrangian description, and we go to the quantization, and we go to interactions, but always in this order. So we always go through the scalar field, the spinor field, and the vector field. So in general, what we found is if you have a collection of fields, phi I. So this is not just a scalar field, it's a collection of scalar fields. It could be the components of a vector, right? My vector will be denoted by a mu, and then this is the normal Lorentz vector with this component, but this is the same, it could be the same, it could be representing this, that the phi is the A and the I is really a Lorentz index. So this is generic. And if this field is now viewed from a different inertial system, then the other guy uses a different field phi prime at the transformed location, which means really the coordinates that this other person gives that location. It's been transformed our location, so that's the x prime is equal to some representation and you take that element that represents this coordinate change, and then times phi j, here's the sum over j, and then x. So this is what we figured out. This is what we wanted. The collection of incidence form in the form that this is a representation. We've been talking about this representation at length, and we know how those finite dimensional representations can be listed. You give two numbers, SL, SR, or spin left, spin right, and these are the ordinary spin quantum numbers, so half integer numbers, 0, 1/2, and so on. So the simplest is if you take 0 and 0, then this is just it is one-dimensional representation. The dimension of this representation is 2SL plus 1 times 2SL SR plus 1. Doesn't fit here. So the dimension of this SL SR is really just the dimension of this representation, and that's 2SL plus 1 in a times 2SR plus 1. This is a one-dimensional representation, which means it's just a 1, so it's nothing. And then you have to call this field a scalar field. And that transforms as this. But you don't have to have an index. G plus I to X. Then we had the next simplest representation. The next one is 1/2. This is now a dimension 2 representation. If you plug this in, and you call this a Weyl spinor. And here I have to leave a little gap, so it's a Weyl spinor field. And that transforms as, so it's called psi, lambda, G, X, psi. It's not psi, it's a 2x2 matrix. The representation is G psi of X. Now, since you could have picked the 1/2 in the second spot, it'll be basically the same thing, just a copy. We have to give this names. And you call it, if it's in the left, on the left hand side, you call it left chiral. Chirality is a term that we invented, that people invented like to say that there are things that look similar, dimensions the same, behavior is pretty much the same, but not exactly. So it's like our hands. Some people call this also left and right-handedness, and I actually dare to call it left-handed last time for our Weyl spinors. It is actually the same thing, but it's better to talk about chirality here. So I'm going to stick with that, even I changed the notes. This is the left chiral Weyl spinor field. It's something that transforms under a certain representation that we call UL. Somewhere I'm going to write what UL is here. Here's my notes. UL is e to the I1/2 angles for the rotations with the rotation generators. They are sigma k half, the spin matrices here, and then plus 1/2 the boost angles or rapidities times those generators. And they are pretty similar, except for they don't have an I, which is significant because of unitarity and things, which I'll discuss. But this is a 2x2 matrix, which goes here. And I suppress the matrix indices. So this is a column. This thing has two components. Maybe I write it somewhere. So this psi is a psi with a psi 1 and psi 2. And I also want to indicate that this is the left one on this field. So this gets a little L. The L is just for left. It's annoying to have an index, to have just a label there when you have to write it many times. It doesn't take any values. It's just allowing us to remember this is left field. So then this is L1 and L2, and the L transforms with the L. In a minute, I'm going to write the same thing again for, well, maybe now, we write the same thing for the other. So we write spiral while spinor field. It's psi r. It's the same thing. It also has two components. But we get an R psi r on the G x equals U R psi L psi R, and it differs by this sign. So the U R is e to the I have alpha k sigma k. So if you perform a rotation on a left or right handed while left or right chiral while spinor, it does the same. It rotates in the same way. But if you boost it, or if you run past it, then one turns this way and the other way. Where's it coming from? Well, I don't know. It is just a possibility that is consistent with the Lorentz symmetry, the principle of relativity, so that in a boosted system, the equation looks the same. And you have the sign isn't fixed. The sign really, the overall sign isn't fixed anyway, because these are just the angles. But they're these two relative signs. Well, this angle isn't, if you switch the angle here, if you switch the sign of this, you also have to switch the sign here. So it's not completely arbitrary. Forget that last comment. You can't absorb it. If you can, of course, absorb it in the eta, but if you did, then you also have to reverse it here. So they exist, the two different things. They might not be realized in nature. In fact, they are, but at this point, we don't know. They're just given as a possibility. And then the 1/2. This is a vector field. And that this is my mu. This transforms as a mu prime, lambda x is the lower transformation for lower index for the covariant one, mu g a mu x. So there, this mixing matrix is really the same as the matrix that sits in here. Or if you prefer, because this is the wrong index position, wrong in some sense. It's of course right, but it usually we have up and down here. So we can write this the inverse mu. So why did it say that this is the right and the other one is the wrong? We started off by here. These were my notes. X mu, the upper one is lambda mu x mu. So transformed. This is where it all starts. Yes.
Why is it now on the right? Or is
that doesn't matter because these are just numbers and these are numbers and there's a sum. But I like to write it there. I had to make a choice there or there because it doesn't really matter, but I had to make a choice. And the reason why I picked it, put it to the right, because then they are adjacent. Looks cuter, but it's absolutely not necessary. And here it's in front because now they're also adjacent there. Very good. So these are the three examples that we're going to discuss. And today we will only talk about the scalar field and the Weyl spinors. And for tomorrow, I haven't decided yet. Yes?
Why is it a mu of g now in order for x mu?
Why is it a mu of g? Because that is a typo. It is this lambda, which depends on the word. Thank you. Yes. And so for tomorrow, I haven't really decided whether we go vector or whether we produce a Dirac field out of the Weyl, it depends on how far we get and what fits in the 90 minutes tomorrow. So to have a nice, so field equations, right? What's that? Field equation, it's the equation of motion, and the equations of motion are in physics are usually differential equations because they need time derivatives so that you know how things evolve in time. And since this is relativistic, if you have a time derivative, you probably also have space derivatives because space and time is all the same thing mathematically. So we'll have to talk about derivatives of these fields. So there's the time derivative, and then there's the spatial derivative, which I write like this. So the number is of course d by dx, d by dy, and d by dz. And since we packaged here time and space into the same thing, so the x mu was ct, and then the x vector, I guess that they also belong. I mean, obviously it does, because my d by dx, I'm differentiating all with respect to the components here, all of them. So then the first one is 1 over c d by dt. It's really it's differentiated with respect to ct, but the c is a constant, so I'm pulling this out, and we have the derivatives in it should be this one. So now it's just a list. It would be cute if that really is a kind of 4 vector, which means that it has a certain property under Lorentz transformation, and it does. It's going to be 1, and we have to figure out which one it is, what it is. It has could be a covariant or contravariant one. So meaning is the lambda like this or like that? And to see this, let's just hit this equation with a derivative with respect to x. So we're getting it here and there. This means, so let's write it first, d by dx and this thing, phi prime I lambda d x equals, it is just a constant matrix, and then a derivative of this x and j. Now here, this is just the derivative of the field. And sorry, this is a bit more complicated. This is the field, well, moved and then differentiated. If I wanted to know the field in the other coordinate system, then I would really write this d phi prime of x prime with some index, and this is the x prime. Like this is how a person in the prime coordinate system would write his derivative of the field, because here g in the original coordinate system just differentiates with respect to the argument. Why all this mess in there? So we need, if you want to know how the derivative transforms, we need to know what is this in terms of this. So now we have to kind of find this object in here. But what is it? This is the derivative with respect to the argument. And the argument is this x prime. So we do the chain rule. This is the derivative of phi I prime with respect to the argument, which I call x prime. Now give me some index mu. And when I'm done, I plug back in what was there. And now the inner derivative is then of the d lambda. Well, it's d by d. Well, it's dx prime mu by d x mu, right? I want it to differentiate with respect to x mu, and this I just put it there, and so on. But this thing, the top person, is the lambda. So this guy, the numerator, is lambda mu rho, I guess, x rho. So take the derivative with respect to x mu, let's do it. So this thing is equal to d by dx mu. How familiar and used to are you to these computations? Like 2 weeks ago, I pretended you had never seen a 4 vector, and now I'm doing stuff with it. But you looked pretty bored 2 weeks ago, so I don't know. Let's test someone. What do we do with this thing?
Lambda nu mu.
Tell us why. Tell us why. What are you doing here?
The numerator is the sum over all row lambda nu row
Right.
x row. So the other for every row which is not mu, the derivative is 0. And
We can do one more step in between. So this is a matrix, but it's just a constant matrix. It has these angles in there, but it's not depending on space-time, not on the x. So this can actually go outside. So we have the lambda in rho, and then dx rho dx mu. Now it's even more obvious what you say. There's the coordinate, and we differentiate with the other coordinate, but the coordinates are independent. If they're different, then why should x differentiate with respect to y give something? Only x with x. So that's a delta. This is what you said. Yeah. This is delta rho mu, and then it's this thing. If you're not familiar with these things, either you have to tell me or you have to tell your teaching assistants. Yeah, I saw that. I hear you. And whenever I do something that's funny, just tell me right here, right now on the spot. So, but this now makes kind of sense, and it's our equation. This I want to keep. It's e I prime I dx prime dx prime mu at lambda gx times this thing lambda mu rho. It was a mu. It's happening here. So this has changed. This was mu rho equals ij e d phi I dx. What happened to my mu? That was here and it's there. I can't copy. Okay, so that's the mu, and that's the mu, and that's that. Now I don't want to have it on the left hand side, so I multiply with the inverse. Then goes to the other side, so it's d phi I prime dx prime. And so that it looks the same, I'm going to write lambda g x. What is this supposed to be? This is the derivative, and that's a field too, and that's its argument. If you don't like it, you have to write it this way, because you might want it as the product or something. Why put a parentheses around it? Because it's not a product, it's the argument. But now it looks like these things, the transform at this new point. Let me just write one sentence. And then the index I have to decide in a minute. Ij g d phi I dx mu x. And now it's the inverse of this. So I have lambda to the -1. And I will probably multiply this by -1 and then mu and then sigma. So this produces a delta. These two together produce on the left hand side a delta mu sigma. So the mu will be the sigma here. And on the other side, it'll just be what it is, mu sigma. And now you can clear it up and use your favorite indices, because sigma is not my favorite. Mu is my favorite, and then the second, my list of priorities comes mu, exactly. So then the mu has to be the summation index. This is just cleaning it up, and this is my favorite, and then we have it here. So that's that. And since we know put the indices around, this is lambda mu d phi I d x mu fx. Boom. So you have these two versions. And this now shows that here the index that came with the derivative transforms covariantly, like a lower index. Even though it's an upper index on the x, it transforms as a lower one. So you have to remember an upper index in the denominator behaves like the lower index in the numerator. So the upshot of this is that the derivative here, this is, you remember, I have to go here. If we wanted to figure out what kind of vector this is, and this is this behaves like a vector with a lower index. So give this thing a name with a lower index. And what people do is they just do del and then a lower index, that lower index. Funny, huh? So you have the x with an upper index at the bottom. So this is kind of one bottom, right? It's an upper index, but you go in the basement. That is as if you were in the first floor or ground floor and you have a downstairs. So that's this thing. You could do the other thing. So like lowering this produces a minus sign here, and raising this produces a minus sign there. So the other is that if you happen to differentiate with respect to the lower index, so bottom is like minus, that's the same as up. Since I wanted to have a nice blackboard, I have to write this again here. This was just messy, but we were talking about derivatives. So the upshot of this discussion is that we should define the d mu as this derivative, and that is 1 over c dt and gradient, and the mu is d over dx mu, and it's 1 over c d by dt minus gradient. And we do this in order to write d prime mu is lambda mu mu, or d prime mu it's lambda mu mu. So exactly what you would have thought for vectors. So the derivatives do the same thing. It wasn't absolutely necessary to go through all of this with this row matrix and everything, but I thought, well, the shortcut is this. You have x prime mu, it's lambda mu x mu. And so if you do what is d by dx prime mu, well, that is it really is just the chain rule. Let's do it this way. Without the prime, then it is the prime by the unprimed by the x prime mu. So this is just a chain rule. Then you use what we have, lambda mu mu, and then d by d mu, and take it to the other side, and then you're there too. So this is just the shortcut. But then you would have asked me, it's not acting on anything. It looks weird. Why would you do the chain rule? How is this helping? does it still work when you apply it? And yeah, so the chain rules is the right thing here because you have an equation that depends on x. But that's x, the coordinate of one person, and then the other person, the other coordinate uses this thing as its her x prime, and then you would have to convert this derivative with respect to the prime coordinate. So I went through this lengthy thing because I thought it makes more sense. But if you have to remember the equation, you don't want to go through the lengthy one, you do the shortcut here. Good. Now we know how the fields transform. It's gone, I guess. And we know how the derivative transform. In fact, if I give you a complicated expression with these indices and vector indices and all of that, then you know the transformation, it is the representation of everything. So here, for example, this object has two indices, the I and the mu. Well, then it transforms the I with this representation, it transforms the mu with this representation. And if I have more indices, and more indices, then you get more of this per index. So I guess we can do everything now. And let's start our inner field equation of motion. Yes.
Question on the left-hand side, we should have rho ij and then del phi j, right? Because we're on the left-hand side, we have
There's my J, thank you. Because it's summing over the J. Oh, yes. Thank you. And there. What am I doing? Yes. So all these indices are soaked up. And then what is there is the same on hopefully on the left hand side. Now, the scalar field, you know probably really well, and we will end up with the Klein-Gordon equation after like 30 minutes or so, and then you wonder, what am I doing? Didn't we have this already? But it will be our guideline or guide for the discussion of the Weyl family. It's going to just get more complicated, so let's do the simple thing first. And so I'm not pulling equations out of, or do I? Somehow I pull them out of there, but I also want to pretend there's a, it's kind of forced on us. This is, I want to pretend that the group theory discussion was worth it and it led us to the equation, that there's not much options. So therefore, let's just start really dumb. What's the simplest differential equation with the scalar field and the derivative? I guess it's this. Right? That's not the Klein-Gordon equation, it's just the derivative. So that's a perfectly good equation. If that was the equation of motion for the phi in my coordinate system, and you run with a constant speed, you would have the same, just with the primes. Why? The left-hand side, you know how it transforms. The d, the prime of lambda, it's not even, this is the x prime, this is equal to, and now let's see if we can do it, it's the lower one. So here, and then there's no index. So it is mu phi x. So if this equation is satisfied, this is 0, then this means this is 0. So we have the same equation. It's a good equation. It respects the principle of relativity. It isn't invariant because there's this matrix here, but whenever this is satisfied, this equals 0, and that's equals 0. So you could say the equation transforms covariantly with this index, but still, it's the same form of an equation. If you use Newton's law, then I use it in mine. So But it's a boring equation, right? What does it mean? It means that the phi needs to be constant. This is 4 equations, and it can't depend on time, can't depend on x, it can't depend on anything. It must be constant. That's it. So group theory allows this, but so what? Then we have a constant field. That would be a particle at rest. Be a little more. So let's do 2 equations. This is the first guess, and it's you know, let's do this. 2 derivative. How does that? This is also a good equation from the relativity point of view, because d prime mu d prime mu phi prime x prime is lambda mu rho is the third one in my favorite list. Lambda mu sigma comes after, and so it's d rho d sigma phi x. So if this is 0, then well, the other way around, this is because they're non-degenerate, they can go the back and forth. So if this is 0, then that's 0, so fine. But it's still not much better in terms of physics, because now the derivative of this object is 0. So all of these things have to be 0, have to be constant, right? Like here, this had to be constant. Now it's the derivative of this, so this object has to be constant for every mu. So it really means, this equation means that the d mu phi is a constant for every mu. But that constant, so for this equation now to make sense for different people, you and me, then the c has to be a different c for you and for me, because when I transform the left-hand side here, I get this lambda, then it's different. So it can't be this literally the same constant vector with some numbers in it. It has to be a transformed one. But I don't know of any vector. There's no vector around. You know, where is this constant vector coming from? So okay, this is also too restricted. Now we are approaching something nice. It's also way too many equations because the indices can be anything. This is really 16 equations. Mu can anything from 0 to 3, mu as well. So 4 possibilities and 4 possibilities. So what we're going to do now is to reduce them again and just pick a combination out of those 16 equations. So I'm building a sum out of these components, maybe some coefficients in front of them. It'll turn out just plus or minuses, but I have to be careful. I can't just pick any combination out of them. So like D1, D2, plus D2, D3, but that's just not going to fly because then they all transform in a funny way. So what I do, I have group theory, haha. I am going to contract these indices with an inverse metric. You see, this was obvious, but I just want to tell the story, the fictitious thoughts. Oh, I have this big equation, it doesn't give us anything, so we go one step further and we contract third trial. But this is wonderful because the transformation now is this. If I transform the left-hand side, so in the other coordinate system, because he uses the same metric. This is an object which holds for everybody, right? This is just some metric, not like expectation. It's d mu prime, phi prime x prime is theta mu, and then what I wrote here, lambda mu rho lambda mu sigma d rho d sigma phi x. And this magic thing is eta rho sigma according to our previous discussion, which you kind of knew. And then it is the same. It's eta rho sigma d rho d sigma. And in fact, since mu and mu are 3, I might even replace them by the nice one. So mu is the same. Now, if this is 0, then if that's my equation, you have the same equation in the other coordinates. So that is a invariant equation up there. And how does it look? It's of course, well, the metric is plus or so it is 1 over c squared P squared minus blah blah phi, and it's the wave equation. And we have really literally come full circle in the discussion. We started with the wave equation following from the Maxwell's equation because we said we want something that is local, and so we have a field that can propagate, and then we ended up with the wave equation. Then we wanted the wave equation to be an equation that holds for every observer. Then we came up with the Lorentz transformation because the Lorentz transformation, although was basically fine to respect this. So, and then we've been talking long about Lorentz transformation, and now we're recovering the wave equation is one of the equations that is invariant in a Lorentz transformation. Not that we put this in at the beginning, but we did, right? But it's nice that we came back here. So you can write this by pulling up the index on the first derivative, a little bit more compact like this, or by definition, we can call this box. This is box. We had box before, but only in 1+1 dimensions. Now, if you see it, it's this guy.
You're looking at square in the wave equation.
Am I losing the square? Yes, thank you. I wanted to write. With this. So many things. I like that you pay attention here because there seems to be typos, a lot of typos in it. You know what this equation describes? Just things that propagate at this speed. But still, I want to discuss this equation even further by going to momentum space. So it's a good point to talk about this. If my phi is a function of Minkowski space x and t, I can also transform this to momentum space, and then the phi is a function of energy and momentum. And here I put minus I p x h bar d4 t. So this is now a definition of this phi tilde. And the p times x, this is the scalar product of the four vectors. So this is p0 x0 minus p vector times x vector. And so this thing is ct. So for this to be t minus p times x, that object is p over c. The zeroth component of the momentum is the energy divided by c, and then this combination is that there, and with this minus I, with the minus I, what we have up here is what you want, right? Minus I dt over h bar plus I p vector times x vector over h bar. I don't know, you can do Fourier transform with either sign, but that's the normal one because this is not something moving in momentum p rather minus p, and the energy always had the one case, the minus. So that's why I like this. Now, plugging this in our wave equation, and first derivative, I'm not sure how slowly. You have to give me some feedback. I'm taking the derivative here, and fold it into the integral, and then it hits the x there. And let's do it once. So it's this thing, and then d mu of the exponent minus ip times x over h bar, d for p, but this is minus I over h bar, and now it's d mu, and here I can write, for example, p with explicit indices, and what's convenient? I'm going to differentiate with respect to x, so here I probably want the index up. So that this becomes a delta. So I want an index up and these two things. Now this is minus IH bar P mu times the derivative, and that's the delta. Delta mu, and least contracted is a mu, minus I P mu H bar. And that makes all sense. Here's a lower index, there's a lower index, of course. Now the second derivative is doing pretty much the same thing. It'll go through, but have an upper index, so I have minus I P mu minus I P mu and e to the minus I P minus x over h bar d for t. All of that stuff is minus p squared over h bar squared. And so if that equation says no, it's zero, then it means that all these Fourier modes have to be zero because they're independent. So for every p that's really independent. You can see this if you multiply so you can see formally by multiplying this equation by I ux and integrating over x. Then you get a delta function in P and Q, and then you perform the P integral, and then you just get something well, where the P is. But you know that the Fourier modes are independent, and then the equation is minus p squared h bar squared phi tilde p equals 0 for all the p's. So separately for all the p's. And there's not even a derivative there, it's just an algebraic equation. And what does it mean? It means if that p phi tilde wants to be non-zero, then this has to be 0. So phi tilde of p non-zero only for the p squared equals 0. The h bar is never 0, mine is also never 0. So it's p squared. This is the 4-vector squared, so that is the p squared over c squared minus p vector squared, and that's 0. So what do we do? Multiply the c up, and it's p squared equals c squared p squared, or take the root 3 is c p vector, and that is the dispersion of the massless relativistic particle. You do this, so you have your waves, and if you go to the momentum space, you have a particle picture, and then you have this dispersion relation. But I'm again going to do this for the Weyl spinors too, and then it's nice to have seen this before. I also want to now add a mass term to make this almost massive. So I'm going to modify the equation. Where's our favorite? This is this equation. How can I modify this? Make it more complicated. We don't want to have another derivative on it because that part is good. So let's. Well, we don't have to guess now. We know how the Klein-Gordon equation looks like. It is so add mass. And go plus something that works as an equal. Yes.
Why could you argue there that the thing inside the integral is 0?
Yeah.
Whole integral is 0.
Yeah, because
You perform a inverse Fourier transform. Then you get like 0 transforms to 0, and then
okay.
on the left you get this.
was it good enough, or shall I write an equation to see what the words?
Yeah, I think I understand it. I do the inverse algebra.
Yeah. So the inverse is this thing is equal to, yeah, this thing is equal to the 0 times e to the plus I dx over x, but that's 0. Oh, this thing is. This works from our transformation point of view, because this doesn't transform at all. It was invariant, like we wrote in this equation, this line, and that's the phi also doesn't transform. So that's a candidate. And you know, now here I'm skipping, you know what number to put there to get the proper equations. It's this m squared c squared over h bar squared, as we did in chapter 1. And the Fourier version of this is here we have minus p squared h bar squared from before, and this stays m squared c squared over h bar squared, all phi tilde 0. That's now in computation. And here it means the p squared has to be c squared. And believe it or not, this is the massive relation, because this was e squared over c squared plus minus p vector squared, and solving this for e means e is square root c squared v squared plus m squared c to the 4. That works. I don't think I can say even more about the scalar field, or can I? Oh yeah, one little remark. Now we could go wild because it works so well. We could just add more and more stuff, not just the phi. We could do anything, like we have this, and now we have this. What's your favorite expression? It just has to have it can have as many derivatives as you want, as long as they are connected, contracted. So there shouldn't be anything open, because then it works. So I can have something like this, 2 phi's and that. And if I'm not happy with 2 phi's, I put 2 more phi's. As I said, I can go wild. Anything works. And that is a relativistically okay equation, because in your system it has the same form as primes everywhere. These nonlinear terms, these are linear terms, because it's just 1 phi per term. Here it's 4 phi's. Those terms with more than 1 will be interactions later, when we'll figure out that these are interactions of the particles. At this point, we don't know what this all means. At this point, I'm just telling you, we'll stick to the linear ones, and these are the free particles with the conserved momentum, this momentum, conserved energy, and everything fine. And then worry about this later, and also have some idea how to select certain interactions instead of writing just everything. Yeah. Now I said everything about the scalar field, and we're going to move on to the Weyl spinors and try to find an equation for them. This was just the warm-up, but so that you're not surprised by the method, we went through it. For 2 Weyl spinor or Weyl field equation. Weyl spinor field, whatever. Weyl. It's a Weyl spinor, right? Weyl spinor field equation. Oh, I didn't say. There's one more remark. Did you like? What did I tell you? Do you have to like the Klein-Gordon equation or not? We discussed it before, in the very beginning, probably the first level. Yeah. And it was, or the second, we had the Klein paradox, right? The Klein-Gordon equation, I taught you not to like, because it has a probability density which could be negative. Whoa. and then we don't have an interpretation for it. So that's why we didn't like it, and we moved on to field theory, and now it's back. Now I want you to like it because it is not, where is it? It is not a quantum mechanical equation for a probability amplitude phi. That's not a probability amplitude. Now we're doing classical field theory. It's just a classical field. And if the classical field has a negative probability, it doesn't matter because there's no probability interpretation in the first place. There's nothing like probability. It's just the value of the field, and the field propagates. So here it's okay. So from now on, you'll like it again, but as a field equation for a classical, in a classical setting, not, you still don't like it, is at least not exactly, maybe approximately, time paradox needed strong potential. So it's sometimes it's okay. It's not good as a quantum mechanical equation, but it's good as a classical field equation. And we'll turn that classical field later, in 2 weeks probably, into a quantum field, and then we'll see what happens to that equation if it blows up in our faces. It won't. Now, okay, stop now. Go. And let's do left first. Doesn't matter. Let's do left first. So psi L. What's your favorite equation? You do psi d mu psi L equals 0, but that's of course too restrictive. It sets both components. Remember, psi L is with psi L1, psi L2. It sets both of them to 0. The derivative acting on this just means derivative here and derivative there, and then it really is just two constant fields. We don't like that. Now we could, in the next step, just say mu, then we blah blah blah, then we contract them, and we have this, and then we're happy. That works. Same story. But this is nothing really new. It just means that this box goes up here and there. Then we have just two lines. Both are scalar fields. This is really nothing new. It's just a copy. The Weyl spinor should be more, could be more. It has the potential of being more than just two independent fields. So instead of contracting these two things, let's play with this index, forget this derivative, and contract these two indexes. The mu, the derivative, with the spinor index, A. That doesn't seem to work because the one is 0, 1, 2, 3, the other is 1 and 2. It's just very different. And now the groups theory business starts. We have to figure out how to connect the two. How do we do this? We really have to remember how the field transforms. So psi L transformed like this. It was the UL, that's right, UL psi L, and then it's e to the I half alpha k sigma k plus 1 half eta k sigma k psi L. Now, the next few ideas are probably feel unmotivated, like where is this coming from? But I'm just studying and like Weyl would have probably studied all of this and then discarded many things, and then what was good he kept, and I'm writing down what he kept. So let's look at what psi dagger L psi dagger does under rotations. So now only rotations, which means only this first bit. So the eta is 0, because that is the nice bit. Why? So this is psi, this is e to the I half alpha k sigma k psi L dagger, like psi L goes to this times pi L. and then the dagger is just the dagger of it, and then we have e to the I half alpha, it's a different sum, L sigma L psi L. Now, this is equal to psi L dagger, and this dagger, and the order changed, and the dagger means transpose complex conjugate, so that I gets minus. The alpha is a real number. Sigma is a Hermitian, it's a Pauli matrix, it's Hermitian, so it doesn't feel the dagger. And then we have that. And then you have e to the plus I half alpha L sigma L psi L. And this is the inverse of that. Oh. Not sick, you don't have, it's just done. That's the inverse of that. Since this is really the same matrix up here, you can pull them together, then the exponents cancel, plus and minus if 0, e to the 0 is 1. So that's really psi L, psi L. Oh, nice. So what does it mean nice? Invariant. Under rotations. So this combination is, yes.
Why can we pull them together? Don't we, like, we can't just.
No, we cannot. If they don't commute, we cannot, but they do.
Okay.
It's the same thing. Baker Campbell Hausdorff says, put them together and then
Yeah.
all the many commutators. But minus I half alpha k sigma k commute with I half alpha L sigma L. You could, you know, the i's go away, and that's the same thing.
Yeah.
So that is 0, and therefore we can put it together. So that's invariant. Now, what do we do? Let's stick a polymatrix in between. Okay, and do the same rotation. Then we have psi L dagger. I use what we found here, e to the minus I2 alpha k sigma k k. That's now L, because this is sigma k. E to the I half alpha m sigma m psi L. So now we're in trouble because they're adjacent. And this doesn't commute with that because it's not the same object. Different ones. So now you should really do Baker Campbell Hausdorff. There is a version of it which has exactly this form, not just the exponential putting together, but with something in between, and the exponential being the inverses of exponents being the inverses of each other, negative, like this thing. E to the x, y, e to the minus x. The formula like this. And it's pretty easy. It's the y plus x with y plus x with x with y plus x with y, x with y, and stuff, and so on. And really like the exponential series, their numbers, this is 1 over 0, 0 factorial, 1 over 1 factorial, 1 over 2 factorial, 1 over m factorial, if these are in commutators. Now, we could waste more time and do this exactly, or for the purpose of today, just keep it simple and evaluate this to linear order in our rotation angles. Just so that we get somewhere. So to linear order, psi sigma k psi transforms. Well, I don't even use the size, do I? Just look at e to the minus I half alpha L sigma k e to the I have alpha m sigma n. Linear order in the alphas. So setting alpha all to 0, then we have sigma k. And then we have here the first order minus I half alpha L sigma k, and this keeping the 1, and now here the first order, and this keeping the 1, then plus I half alpha m, the sigma k has to be on the left of the sigma m, you know. And then plus order alpha squared. And now use something that you have to remember in all of this. So I, J is I, epsilon I, J, K, sigma K plus delta I, J, 2 by 2 identity. So this is your friend whenever you do Pauli matrices. So what it means is two different Pauli matrices give you the third with an I and then cyclic, and to the same, don't have this term, but square to 1. The same, this is square, so square to 1. Now, if these are the same, oh God, let's write this. Sigma k minus I half alpha L. Now, epsilon L k to m. Let's do m, and then sigma m, and then there's an I. So that is the first term here, and plus minus I half alpha L delta L k. Now down here, plus I half alpha m I epsilon k m L sigma L. I'm sure that put myself in probably all picking L, it's a dummy mix, but and then plus I have alpha m delta k m, and now you see that these two cancel because this thing sets the index to k, and this is the index k as well, and then we go away. So we have this, and they two are supposed to add up to the same. Okay. So this is easy to see my k. So we have mine plus 1/2 alpha L epsilon L k m sigma m. Now I want to see that this is the same. I'm going to see that. So there's the minus 1/2. I times I is minus 1. And since here's an alpha L, let's turn this m into L. There's an alpha L, and therefore this needs to be an L. But then that can't be an L. Let's say this is an M then. And this has to be an M. And that K is a K because it has to be, it's the K that we had here that we wanted to transform. But now hopefully, if you turn these two around, because the epsilon is antisymmetric, there's a minus sign which makes a plus here, so it's the same as that. So this is equal to sigma k plus alpha L epsilon L k m sigma n. Whoa. And now this I want to write as something sigma n. The second is already there, alpha L epsilon L m L k m. And the first one I have to set to k. I'll do this. So that I can write as a matrix R km sigma n. And R is this. But that looks like this thing. The R Kn is the diagonal is 1. And then if it's not diagonal, like this is could be 1, 2, and that's 3. So in 1, 2, it's 3, alpha 3. In 2, 1, it's minus 3, alpha 3. In what? 1, 3, we have minus alpha 2. Then we have alpha 2 here. And in 2, 3, that's 1. This is how this thing looks like. But since I have neglected my second and so on order, I don't. It's the same. It's a rotation. It's basically what I'm saying. It's a rotation matrix to first order in the angles. So the real. It actually works if you do everything. Then you get the rotation matrix that rotates the vector sigma. So the sigma, basically the sigma m, the three components are really like a vector. Sigma 1, sigma 2, sigma 3. These components are mixed together. So we have a Pauli matrix to left and right with these Weyl spinor rotations do the same as if you rotate the index on the sigma. Let's write this down because it's so amazing. So e to the minus I have alpha L sigma L sigma k e to the I half alpha m sigma m is equal to rotation matrix k m sigma m. It even deserves this. So don't forget what we were doing. We're doing this psi dagger L sigma k psi L transformed under rotations as this rotation matrix A R K M psi dagger L sigma m psi L. This is a nice formula, but that was the point. This combination is a vector. The one without anything in between is a scalar. It doesn't transform. So if you have something that doesn't transform and something that is a vector, then you know, look at this. E doesn't transform under rotations, of course, and X vector transforms under rotations like a vector, and you put them together to produce a 4 vector. So I am claiming that this combination psi dagger L psi L psi L dagger sigma k psi L is transformed as a 4 vector. This is now 4 things, but I didn't write the 4. I just wrote dagger, and I mean 1, 2, 3. So you have a list of 4 things, and I'm claiming, at least it's suggestive, that these 4 objects transform as a 4 vector. Why do I think that? Because under just the rotation part, they do. A 4 vector under rotations, nothing happens here, and this is just mixed by rotation matrix. Boom. So that's the same here. If that's not really it.
But it's all just to linear order, right?
No, here I gave you to linear order.
Yeah.
But had we done everything, it would be exact.
So then
But it's just an
this
all.
RKM is like different from the one that you're on the left showing, or?
It's the same now.
Okay,
I
see, yeah, I see.
take everything else.
Okay.
So this is now a real rotation matrix, unitary, what is orthogonal, so the dagger is the inverse, which isn't the case here. Only to linear order. Right. Of course, this is very naive. I haven't done anything with the boost. I have to know whether under a boost they mix in the right way. This is rotation, fine. I can write anything. I could have written my name, doesn't transform under rotations. Although this looks better than my name. We'll still have to see how also, we don't know if this is a vector or a vector. You know, is it covariant or contravariant? No idea. They both do the same. And there's not much difference in and contravariant. It's just plus minus. Which one is it? So we have to do more. Now we look at the boosts. And also, because we don't have infinite time, we just do boosts in one direction, and your favorite direction is the third direction, the z direction, because then the matrix sigma 3 is the nicest. In any other direction is okay, because we know that we can rotate. We have done the rotation, so if you wanted to rotate boost in a different direction, you just rotate first to a different direction to the z-axis, then you boost and you go back. So it's not even a restriction at all. So say you have a boost in the three direction. So in the z direction. What does that look like? So that is mediated by half eta is the boost parameter sigma 3. Eta doesn't get the 3, it's just one. It's just one input. One object. Okay. Well, we can still boost it. Psi L bigger, psi L boosts like this. Psi L bigger e to the, do we need to do this slowly or? Does that make sense? If you have psi L goes to this, now dagger this business, and the dagger ends up here, they change the order, but that's real and that's Hermitian. So it's the same. It's not unitary. If it was unitary, so if this was the inverse of what we had, we would have to flip the sign. That's what's done by the I, but there's no I. So that's what it is. And then we have e to the 1/2 eta sigma 3 psi L. These are the same, I can put them together. So that's equal to psi L e to the eta sigma 3 psi L. In fact, I said sigma 3 is so nice. I'm not even perform this. I expand it to linear order again. So that is psi L dagger psi L plus eta psi L dagger sigma 3. What do you think? Is this good? Is this bad? Now, that top component here, this thing, under boost in the z direction, produces that. Is it good or bad? Good, exactly. Why is it good? Let's see what the boost did to our time, right? T prime is essentially like the gamma t. The gamma you don't see in the first one, so it's the gamma t, and then minus v x. So in the z direction, it's z squared. Right? So the time, the zeros component, the new one is mixed with the direction. It's the z component of this. So the third component, and that's there. That's why you were happy, because it has mixed the time with the three component. Now the x prime, the z prime is what is it? Z minus vt. Now we want the mixture with the t. So if we do psi L, sigma 3 psi L, this, then we get psi L dagger e to the 1/2 eta sigma 3 e to the, oops, that's sigma 3 e to the 1/2 eta sigma 3 psi L. Now again, oh, this is easy because the sigma 3 and the sigma commute. So I bring it to the other side, and then I have psi L dagger e to the eta sigma 3 psi L. Now the same expansion, and we have a 1 here, but there's an extra sigma 3. And then the next term is eta sigma 3. What is sigma 3 times sigma 3? You're listening? Sigma 3 times sigma 3. Exactly. So then we have plus psi L dagger psi L. Isn't that amazing? Now, the third really stays the third and gets more time component, the zeros component. And even with the same sign, like a rotation would have different signs. You take one a little bit away and you add to the other one. But here it's plus, plus, exactly like here. The be the same sign, yeah. Exactly right there. So we are in good shape. If we can show that they are the same and that's the same. So let's just do it. If we have psi dagger L, sigma K, psi L, where this is not 3, but 1 and 30, 1 or 2, then it looks a bit like this. It looks like go to psi L E. What do we expand it? Let's expand it straight away. So this is 1. That's e to the 1/2 eta sigma 3 sigma k eta 1 e to the psi L. So that's I just inserted. Now expand psi L sigma 3 sigma k. That's the first term. And then comes here the linear order 1/2 eta sigma 3 sigma k, and then here the linear order sigma k sigma 3 plus the higher orders. But now, since they are not the same, this is not the same, k is not 1 or 2. If it was 3, then we would really be back there. Where's my eta? Nobody noticed that the eta was gone. Here's the eta, and here's the eta gone. Here's the eta. This is the velocity. The eta. Well, anyway, then if this was 3, we'd have the same we had there, square and half the size is 1. But if it's not the same, say it's 1, then sigma 3 times 1 is sigma 2, and sigma 1 times sigma 3 is minus sigma 2. And plus and minus 0. So then we have psi dagger L sigma K psi L. So indeed, they don't transform. If now we're ready to believe everything. We believe it's a 4. Oh, is it covariant or contravariant? What do I know? What's the rotation matrix? What's the matrix that does that? So if so psi dagger L psi L, and then here's psi dagger L sigma K psi L. This turned into psi L psi dagger L sigma K psi L. Can we get this? Can we get this? So that didn't change, but it get contributions from here, which was the eta. It got eta here, and 1 and 2 didn't change, and there's another 1. So that's this matrix that makes our proposed four vector. And it does look pretty much like the K Z. It looks like the KZ, however, not quite, because K well, it really is, it's the group. It should look like e to the I eta KZ. That's what it's supposed to look like. And K Z was this thing, 0, 0, 0, I, 0, 0, I, 0, 0, 0, 0, 0, 0, 0, 0, 0. So this two linear order means what? This thing to linear order has the one along the diagonal, and then we have I times eta times this. It's minus eta minus eta. So this is minus eta minus eta. So that generator, the Lorentz generator for a boost in the three direction, looks like this. But we get this. What is it? It means it's the inverse. It's the wrong thing. It's the inverse. So we have this. So that's not our lambda, but it's lambda inverse. With the minus sign, it's the inverse. So if a vector transforms with the inverse, it's an upper or down. It's covariant or contravariant. Thank you. So last equation. This object here, psi L, psi greater L, sigma K, psi L, transforms like the guy with the downstairs index, because W prime mu is W mu lambda to the minus 1 mu. If you have something downstairs, and that's exactly what we see here. This is now has now moved to the right because it can, and this could. This is matrix multiplication. And so if this is a four vector, so let's define sigma mu. Oh dear, let's define sigma mu as the identity and the sigma vector, where the sigma vector is what we had before, the two components. I'm doing this because then that object here is psi L sigma mu psi L. And then you see that it has a lower index mu, and it's all beautiful, just visually beautiful. And performing the rotation or any Lorentz transformation, it could be a rotation or a boost, this thing behaves like a four vector. And this is, you see where we're going. We have now a connection between the four vector and the spinor indices for tomorrow. And now just one very little thing, a notation that comes out of nowhere, there's to be bar over it. Later we'll have one without the bar, and this happens to be the bar. Why would you introduce a bar if there wasn't any conflicting thing yet? But the convention is that this is a bar. We'll continue there tomorrow.
Muss das von